Welcome back. In this video, we extend simple linear regression to the case of multiple independent variables. When more than one independent variable is involved, we call this multiple linear regression. The multiple linear regression model expresses y as a linear combination of p independent variables, x1 through xp, plus an intercept and an error term. Let's walk through each piece. Y is the dependent variable, what we're predicting. x1 through xp are the p independent variables, also called predictors. The beta coefficients from beta 0 to beta p are the parameters, and epsilon is the error term, capturing variation not explained by the model. Notice that when p equals 1, the formula reduces to the simple linear regression model. Before we start discussing formulas, let's visualize what two independent variables and one dependent variable looks like in three-dimensional space. The bottom axes represent x1 and x2, our two independent variables. And the vertical axis represents y, the dependent variable. Each white dot represents an observed data point, a specific combination of x1, x2, and y values from our sample. The blue checkered surface is the fitted regression plane. It shows the predicted value of y for every combination of x1 and x2. Instead of a line, like in simple linear regression, we now have a plane. The yellow lines are residuals, the vertical distance from each observed data point to the regression plane. A shorter line means the model predicted that point well. Longer lines indicate larger prediction errors. Similar to simple linear regression with a line of best fit, the method of least squares finds the plane of best fit that minimizes the sum of squared residuals. When we have more than two variables, it becomes difficult to visualize all pairwise relationships at once. A scatterplot matrix solves this by showing every pair of variables in a grid. Here is a scatterplot matrix for 4 variables. The diagonal cells show the variable names. Each off-diagonal cell is a scatterplot of the two corresponding variables, the row variable on the y-axis and the column variable on the x-axis. For example, variables 1 and 2 show a strong positive linear relationship. As one increases, so does the other. Variables 1 and 3 show a negative linear relationship. They move in opposite directions. Variables 1 and 4 show no apparent relationship. The points are scattered randomly. Notice the matrix is symmetric along the diagonal. A version showing the lower left half of the matrix is called a half scatterplot matrix. The pairwise correlations can also be summarized compactly in a correlation matrix. Each entry shows the Pearson correlation coefficient between two variables. Notice that the diagonal values are always 1. A key limitation of both the scatterplot matrix and the correlation matrix is that they only capture pairwise relationships, not how all variables interact jointly. Now let's talk about how we estimate the regression coefficients. Just like in simple linear regression, we use the method of least squares. The estimated regression coefficients, beta hat 0 through beta hat p, give us the fitted equation. We use this to predict y hat for any combination of x1 through xp. The residual sum of squares is the sum of squared differences between each observed yi and its predicted value y hat I. This is identical in spirit to the simple linear regression case. Expanding the squared term, each residual is yi minus the full linear combination of predictors evaluated at observation I. To minimize the RSS, we take the partial derivative with respect to each beta j and set it to 0. This produces p plus 1 equations with p plus 1 unknowns, one for each coefficient, including the intercept. As with simple linear regression, knowing how to solve these equations is not required for the exam. In practice, statistical software handles this automatically. To estimate sigma squared, the variance of the error term, we use the mean squared error, or MSE. This is the RSS divided by n minus p plus 1. The denominator is n minus p plus 1, where n is the number of observations and p plus 1 is the number of estimated parameters, the p-slopes plus the intercept. In simple linear regression, this was n minus 2 because there were only 2 parameters. The residual standard error, or RSE, is defined as the square root of the MSE. It estimates sigma, the standard deviation of the error term. A smaller RSE means the model's predictions are closer to the observed values on average. The multiple linear regression model can be written more compactly using matrix notation, especially when there are many independent variables. We define 4 objects. First, a response vector y, a design matrix x, a coefficient vector beta, and an error vector epsilon. The response vector y is n by 1, containing the n observed values. The design matrix x is n by p plus 1. Each row is one observation, the first column is all ones for the intercept, and the remaining columns are the predictor values. Multiplying a column of ones by beta 0 just gives beta 0 for every row. The coefficient vector beta is p plus 1 by 1, stacking beta 0 through beta p. And the error vector epsilon is n by 1, one residual per observation. These 4 objects let us write the entire multiple linear regression model in one compact equation, y equals x beta plus epsilon. Minimizing the RSS with respect to beta gives the ordinary least squares estimate. Beta hat equals x transpose x inverse times x transpose y. This is the cornerstone formula of multiple linear regression. One important requirement is that x transpose x must be invertible. This fails when predictors are perfectly correlated, a condition called perfect multicollinearity. To make predictions, we multiply the design matrix x by beta hat. Substituting in beta hat, we get the following formula on the screen. The matrix x times x transpose x inverse times x transpose is sometimes called the hat matrix, represented by capital H. It is called the hat matrix because it puts the hat on y through the equation y hat equals h times y. Thanks for watching. For a comprehensive written course, hundreds of practice problems, progress tracking, and AI-assisted tools, visit the Actuarial Nexus. See you in the next lesson.